Hi, I'm Dr. Jeff Groh, and this video is about mirages and the mathematics behind them. Just about everyone has seen a mirage where, looking down towards the ground at some distance, you seem to see what looks like water. What you're really seeing is the sky. Light coming down through these dense layers goes through less dense layers if the Earth is really hot. The hotter it gets, the less dense the air near the surface will be. The light will tend to bend towards the more dense regions, so it'll tend to bend away. And so when the light is coming up, it hits your eye, and it looks like that blue, looks like blue water. It looks like it's down on the surface of the Earth, but in fact, it's coming from the sky. A mirage is just a refraction of light through a substance that has variable index of refraction. There are many such phenomena besides the oasis that we have just described. At sea, there is the famed Fata Morgana, based on something of the opposite principle, where you have cool air. You may have a boat here, and light reflected off of the boat may travel through layers with less density, curving the light perhaps back towards the Earth. So from the perspective of a viewer, it looks as though the ship is in the sky, which can be rather confusing. In addition, around the sun has a corona kind of atmosphere around it, with the density of material becoming less and less as you move away from the surface of the sun. Light traveling from a distant star might hit the corona and travel through those regions with variable density and hence variable index of refraction. And light could be bent as a consequence. So the observer, standing over here on the Earth, will believe that the star comes from over here, when in reality it comes from over here. Now this is a huge exaggeration. The amount of refraction through the solar corona is actually quite a bit smaller than this. But this problem sparked my curiosity when I was a high school student. I wondered if maybe Einstein had gotten something wrong, and that the gravitational refraction that he refers to from the general theory of relativity was just mistaken for refraction of light through the solar corona. But it turns out I was wrong. I later did a more in-depth study of the issue after I learned a little bit about general relativity, which was impossible when I was in high school. And I've learned that, in fact, when you're far enough away from the solar corona, gravitational refraction is by far more important in the refraction of light around the sun than refraction through the solar corona. it's possible, if you're just really close to the surface of the sun, that refraction could be more than the refraction caused by gravitation. But for most cases, when you can actually observe the light, the gravitational refraction is larger. Another interesting example is refraction of light through the atmosphere of the Earth. The Earth has an atmosphere that gets less and less dense as you go out. Light can refract through the atmosphere, changing the apparent position of the sun. The sun may appear to be over here, when in fact it's over here. It is even possible that the light ray can bend around back to where it is night, and it will appear that the sun is still up even after the sun has actually set. In mid-latitudes, in fact, the sun appears to set 2 minutes after it has physically dropped below the horizon due to this refraction effect. Most high school students learn about something called Snell's law, whereby you have an index of refraction n1 times the sine of the angle of incidence is the index of refraction n2 times the sine of the angle of refraction. The idea here is this is kind of a boundary between two substances with different indices of refraction. You might have a light ray coming in, striking at some angle, theta 1, and then being refracted at a different angle, theta 2. That will depend upon the two indices of refraction, angle of incidence and angle of refraction. What is this index of refraction? The index of refraction is the speed of light in a vacuum divided by the speed of light in a particular substance. Light is an electromagnetic phenomenon, and it's affected by the electrons in a substance. And so light can be slowed as it goes through a substance. So there's the speed of light in a vacuum, which is a universal constant, divided by the speed of light within a particular substance. As you can see, there's a sudden change in that speed of light here at this boundary between two different substances. For a mirage, you don't have a single index of refraction because you don't have a nice simple surface. There's no one single surface, which is the boundary between two substances having distinct indices of refraction. So in fact, the index of refraction will be a function of the height above the surface of the Earth in the case of a mirage, because the velocity will depend upon where you are in relation to the surface of the Earth. This will change in a nice smooth way as you go away from the surface of the Earth. What we seek to do here is to generalize Snell's law to the case where we have a continuously variable index of refraction. The easiest way to proceed is by using the principle that light takes the path of shortest time. Since the speed of light will vary continuously between different points A and B, it may be that the shortest time path is not the straight path between the 2 points, may not in fact yield the shortest time for light to travel from point A to point B. If we have some path from point, let's say, x1 to point x2, that path can be described as a function of t. We can go in three-dimensional space if we want. The velocity will be denoted by the vector v, which is the derivative of the position vector, and this speed is the norm of the velocity vector. We're going to denote the speed by a lowercase letter v, as opposed to v with an arrow over it, which is the velocity. Velocity is a vector, speed is a scalar. So the speed is the length of the velocity vector. The speed can be calculated two ways. We've just shown how speed is the norm of the velocity vector. So if you know the velocity vector, you can calculate the speed by just calculating the norm. But it should, in principle, be possible to calculate the speed as a function of the, say, height above the ground. So v should be also a function of your position in space and should not necessarily depend upon time. So this could be known theoretically in principle as a function of where you are in space, independent of time. But it's also calculated as the norm of the velocity. So to calculate the total time, that the light ray is traveling between point A and point B, what we'll do is we'll integrate along that curve the element of time. That gives us the total time. This type of integral, the path integral, is the kind of integral that we introduce in Calculus 3. There's two ways of calculating the velocity. We can use the norm of the velocity vector, and we can also use this function v, which only depends upon x, y, and z, the speed of light which is known at each point. We're going to evaluate this function. Notice that this is the speed and this is the speed. These cancel out. And so we're really just adding up elements of time. But this expression is going to tell us how to find the curve that gives you the minimum total time. What we're trying to do is find the curve, C, that gives you the minimum total time. The norm of the velocity is the norm of dx dt squared plus dy dt squared plus dz dt squared, and we're divided by this function here, v, which depends only on x, y, and z. As a bit of notation, dx dt is often denoted by x with a dot. The dot above the variable represents the derivative of that variable with respect to time. So similarly, y dot is, by definition, dy dt. This notation, using dots for derivatives with respect to time, is due to Sir Isaac Newton himself. So in fact, the problem of finding the path by which a ray of light travels between point A and point B through a substance with a variable index of refraction is equivalent to finding the minimum time, finding the path that gives you the minimum time. So this is the minimum over all curves, C, of the expression the square root of x dot squared plus y dot squared plus z dot squared divided by v of x, y, z dt. That will minimize the total time of transit. How do we minimize such an integral? There's a famous theorem, an equation, that results from an analysis of these sorts of problems. It's called the Euler-Lagrange formula. So to solve this problem for the path that gives you the minimum transit time, we'll need to take a look at the derivation of the Euler-Lagrange formula. Suppose that we have the following problem. We want to minimize the integral along a path of some function that involves an independent variable, let's call that independent variable t, y of t, and y dot of t, where y dot is the derivative of y with respect to t. We want to minimize this to find the path that gives you the minimum value of this expression. This expression takes this function and gives you a scalar number. Such expressions are called functionals. We're not assuming this function here is linear, and so this will not be what is called a linear functional. In all likelihood, it'll be nonlinear as a functional. And so these kinds of problems are special. They require a lot of detailed analysis to solve. Suppose we have an optimal solution. This curve will give the best solution. This is t, and this is y. So this is going to be t1, and this is t2. This is the optimal solution, the optimal path. What we'll do is deviate from this path by some amount. We'll deviate by some amount called epsilon. Let's suppose that we denote our optimal path by y hat. This less than optimal path we'll denote by y. It's going to be the optimal path plus we'll have some scalar lambda times this little error. By changing lambda, we can take paths that are in between these two, or perhaps even farther out, if lambda is bigger than 1. But one thing we must agree upon is that epsilon, this little deviation, must be 0 at the endpoints. Epsilon at t1 will be 0, and epsilon at t2 must also be 0, so that all of these paths begin and end at the same place. Now, I will depend upon the epsilon and the lambda. We're going to have this less than optimal I, and since we're integrating on this particular path y, this will go from t1 to t2. We'll have y hat plus lambda epsilon, and then for the derivative, it's y hat dot plus lambda epsilon dot. Now, we're supposing that this y hat is the best solution. So we expect that if we take the derivative of this version of I with respect to lambda and evaluate at lambda equals 0, we should get 0. We should not have the optimal I, the minimum I, if we perturb off a little bit from the optimal path in either direction. And so the derivative of this functional I with respect to this little perturbation value lambda at lambda equals 0, which means on the optimal path, should in fact be 0. Let's see what happens. We have this derivative with respect to lambda, and we will evaluate at lambda equals 0. But the derivative is of an integral. We're going to have this y and this y dot, and then we're going to evaluate at lambda equals 0. How do we do this? The derivative can be moved into the integral. And so we have the integral from t1 to t2 of the derivative of this function of t, y dot. Keep in mind that y is the optimal solution y hat plus lambda times epsilon, where y hat and epsilon are functions of t. Lambda is just some scalar parameter. Using partial derivatives, we'll have the partial derivative of f with respect to t times dt d lambda. Well, t doesn't depend upon lambda, so this derivative will be 0. Plus the partial derivative of f with respect to y times dy d lambda. The derivative of y with respect to lambda just leaves epsilon, plus the partial derivative of f with respect to y dot times the partial derivative of y dot with respect to lambda. Well, y dot is y hat dot plus lambda times epsilon dot. And so the derivative of y dot with respect to lambda is epsilon dot, the derivative of epsilon with respect to t. We're now going to use integration by parts on this last term. In integration by parts, you have a u part that you wish to differentiate, which for us will be df dy dot, and another part that you would rather integrate, which for us will be the d epsilon dt. So the derivative of u, and these derivatives are with respect to time, du dt, we'll move the dt over. We'll get the derivative with respect to time of the partial derivative of f with respect to y dot times dt. V will be the integral of the right-hand side, which is just epsilon. Keep in mind that we're evaluating at the end at lambda equals 0. Also, our non-optimal y will be the optimal y plus lambda times epsilon. So when we evaluate at lambda equals 0, we'll end up with our optimal solution. Now, with this integration by parts, we'll have the integral from t1 to t2 of df dy times epsilon, and then that's times dt. With the integration by parts on the last term, we'll have uv, which is df dy dot times epsilon, minus the integral from t1 to t2 of v du. That's the derivative with respect to time of the partial derivative of f with respect to y dot times epsilon times dt, evaluated at lambda equals 0. Remember that the little perturbation epsilon has to be 0 at the endpoints. So when we evaluate epsilon at t2 or at t1, you must get 0. So this whole term goes away because of these boundary conditions for this epsilon. The only thing that's left now can be combined into a single integral. What we'll have is the partial derivative of f with respect to y minus the derivative with respect to time of the partial derivative of f with respect to y dot, all times epsilon of t dt, evaluated at lambda equals 0. Evaluating at lambda equals 0 makes everything in sight, makes all these y's, in fact, optimal solution y bar. What is more, because this must be true for any epsilon, this has to be equal to 0 for any epsilon, it turns out this part of the integrand must in fact equal 0 by something called the vanishing integrals principle. If there were some part of the domain where this first factor in the integral was not 0, you could change this epsilon to just pick up that one little place where this function is not 0. In which case, there's no way you could get an integral equal to 0 there. It would have to be something else. So we deduce then that df dy minus the time derivative of df dy dot must in fact be 0, and this is the famous Euler-Lagrange equation. So to repeat, we have the Euler-Lagrange equation. If you have a nonlinear functional of this form, the function y that gives you the minimum value for that functional will have to satisfy this equation. The integral we are working with is slightly more complicated. We're dealing with the total time. It'll have an initial time and a final time, but we have more than just a y and a y dot. We have an x dot, a y dot, and a z dot. And we're trying to minimize this nonlinear functional. Our function here, sure, it may depend upon t. In fact, t doesn't appear there. It will depend upon x, y, and z, but also upon x dot, y dot, and z dot. So it's slightly more complicated, but the equation that you get is very similar. For reasons of simplicity, if we use x, y, instead of x, y, and z, we'll use x1, x2, x3 instead. The equation that we'll get is df dxi, I being 1, 2, or 3, minus the time derivative of df dxi dot, one of the dots of these other variables. This will give us 3 equations that we'll have to solve instead. So if my function f is the square root of x1 dot squared plus x2 dot squared plus x3 dot squared divided by v, which is a function of x1, x2, and x3. This will be the speed of light at different heights, which you might be able to come up with a formula for on theoretical grounds from the beginning. Let's do the x1 case first, the one index case first. We'll have 0 equals the derivative of f with respect to x1. x1 appears here. This is x1 dot, not x1. So I have this function. I'll have this square root of x dot squared plus x1 dot squared plus x2 dot squared plus x3 dot squared in the numerator, which stays the same. As you know, the derivative of 1 over x is negative 1 over x squared, but we have to multiply by the derivative of v with respect to x1 minus the time derivative of the derivative here with respect to x1 dot. The 1 over v is not going to be part of this. I'll put the 1 over v here. The derivative of the square root is 1 over 2 times the square root. But by the chain rule, we have to multiply by the derivative of the inside, which is 2 x1 dot. There are some things we can do to simplify this expression. Clearly, we can cancel a couple of 2's here before using the product rule to calculate this derivative here. Also, notice that the expression in the numerator here is the same as the speed in the denominator. So we could cancel. We'll have 0 is negative 1 over v times dv dx1, and then minus, now we'll have to use a product rule. By the same reasoning, this is also another representation of v, speed, times another, so we have a v squared here in the denominator. When we take the derivative, we'll be taking the derivative of 1 over v squared times this x1 dot. So what is it? Well, the derivative of 1 over x squared is what? Negative 2 over x cubed. So we should have negative 2 over v cubed times v dot, all times this x1 dot, plus 1 over v squared times the derivative of x1 dot with respect to time. That's x1 dot dot. And so we have this negative 1 over v dv dx1 minus minus is plus 2 v dot over v cubed x1 dot. We'll distribute the negative minus 1 over v squared x1 dot dot. I want to multiply both sides by v squared. So that I'll have 0 equals negative v dv dx1 plus 2 v dot over v x1 dot minus x1 dot dot. I'll move this one to the other side. x1 dot dot is 2v dot over v x1 dot minus v dv dx1. That's one of the three equations. The other two will involve x2 and x3. Remember, our position vector is xyz, or x1, x2, x3. The velocity vector is the derivative. That's x1 dot, x2 dot, x3 dot. And so when I have x1 dot dot, that's the first coordinate of the acceleration vector. The acceleration vector is dv dt. So the acceleration vector, if I put this in the first coordinate of the acceleration, we'll have corresponding equations for x2 dot dot and x3 dot dot. If we put them all together, we end up with the derivative of the velocity vector equals twice v dot over v times our velocity vector minus the speed times, now the vector of partial derivatives is the gradient of the speed. And so we'll have the gradient of this speed here. We're almost done. The one thing that we need to deal with is this v dot right here. V dot is the time derivative of the speed. But remember, our speed v was some function of position, x, y, and z. And so we should really rewrite this as dv dx 1 dx1 dt plus dv dx2 dx2 dt plus dv dx3 dx3 dt. And this expression looks like this vector, the gradient of v, the speed, dotted with the coordinates of the velocity vector. And this will give us the final form for our generalized Snell's law for light paths going in media with variable index of refraction. The formula that we seek is the derivative of the velocity vector is twice the gradient of the speed dotted with the velocity vector divided by the speed times the velocity vector minus the speed times the gradient of the speed. In this case, we're given v as a function of x, y, and z. It may depend upon the distance from the center of a star or the distance off of the surface of the Earth, depending upon the application. It will be some given function where we'll know what the speed of light is relative to the position of some stationary object. The actual light ray follows on the path of this vector-valued function, v with a half arrow over the top, and it will have to be the function that satisfies this system of differential equations. Since velocity has three components, this differential equation will end up representing three differential equations, one for each of the coordinates. This one equation will govern the path of a light ray for a mirage, for a fata morgana, for bending of light through the solar corona, for light bending through the atmosphere of the Earth that makes it look like it sets 2 minutes after the sun has physically dropped below the horizon. This one formula will govern all of those things. So this is a true generalization of Snell's law. It doesn't look very much like Snell's law. So we might ask the question, does this imply Snell's law? How can we get Snell's law from this generalization? And I'll show you how. Snell's law is essentially the invariance of the sine of the angle divided by the speed of light. In other words, it's kind of like saying 0 is the time rate of change of the sine of theta divided by v, where both the speed of light and theta will be functions of t when evaluated along a path, the path that light actually travels. In this case, we'll assume that we have a boundary between two substances having different indices of refraction. The light ray will come from over here with some angle theta 1 and depart at some other angle theta 2, like this. So we'll suppose that the velocity is a function of x alone. So it'll have this v of x 0. It'll be some function here alone. It'll have different velocities. It'll depend only upon x. In other words, the partial derivative of the speed with respect to y will be 0. So this gradient has 0 for the second coordinate. Remember that the numerator here was v dot. Let's multiply both sides by the integrating factor 1 over v squared. That's going to go on both sides. And what we'll end up with, if we move this term to the left, is 1 over v squared dv dt, and then minus 2 over v cubed v dot v. That's still equal to this minus grad v over v. We'll cancel one of the v's here. On the left-hand side, what we end up with is something that we can rewrite as the time rate of change of v divided by v squared. The velocity vector will be the speed times a directional vector, cosine theta sine theta. So on the left-hand side, we can rewrite this as the time rate of change of the following: cosine theta over v, sine theta over v. This v up here will cancel one of the v's down here, leaving a v to rescale each of the coordinates of this directional vector, keeping in mind that that's equal to minus dv dx, comma 0, divided by v. If we equate coordinates, the derivative with respect to time of the first coordinate will be equal to the first coordinate on the right-hand side. Derivative with respect to time of the second coordinate will have to equal the second coordinate on the right-hand side, which gives us the invariance of this sine theta over v, v being the local speed of light. So this doesn't change with time. So on each side of our refraction boundary, you have to have the same value, even if you have different angles, theta 1 and theta 2. So we deduce then that in this discrete case, where you don't really have a derivative, this will still have to be invariant on each side of this boundary. So you'll have sine theta over v1 must equal sine theta 2 over v2. And that's the traditional Snell's law. So we have achieved a generalized Snell's law. The acceleration vector is twice the gradient of the speed, the local speed of light, dotted with the velocity vector over the speed, times the velocity vector, minus the speed times the gradient of the speed. We can use this one equation to solve a large number of problems, as we've seen. We'll leave it for another video to actually go through applications of this equation.